Good morning to all of you. We were looking last time a single ended DFAM and we were trying to show that this single ended DFAM, one of the gate inputs of a p channel device, a gate of that is connected to one of the output, which is Vout1, and that makes it single ended. We also have derived from this by a variety of ways that this Vp remains constant, so AC, for AC that can be treated as ground. So this is what we did last time. I will just show the last equivalent circuit which I drew. What we said last time, that since Vout1 is an AC output, for M4 that is acting like an input, okay, because connected, since it is connected, this will act like an input, and since this is equal to of this value, so there is an input signal for M4 and there is an input signal for M2, and we say since both have the same output resistance, this RO parallel this or this parallel this for this output, at the node both transistors are give RO parallels, and therefore ROP parallel RON is always at the output resistance, independent whether you drive from here or you drive from here, and if you superimpose on them, the output net Vout can be obtained. That is what we discussed last time, and we derived finally a equivalent circuit, which I just want to do it again, show you again, that for the M1 M3 side you have a GM VID by 2 RO1 RO3 parallel GM3, and this is GM3 may dominate because it is a diode connection there, and therefore this may actually dominate over RO3. However, as I said, VO1 output is VGS4, and that is further used here in the M2 M4 side, and we say it's a GM2 VID by 2 RO2 RO parallel, again I said it, but this again GM4 will be neglected because this will dominate, and then this is the next source coming from the other input at the M4, M4, and then if I, since I use the same ROs both, so I can directly add or subtract the currents and then put across this resistance to get the output voltage, which is essentially doing superpositions. Okay. You stop this, get a drop, stop this, get a drop, add up. Okay. Okay, so this was what last time we did. So let us look at the actual values, actual expressions. Since VGS1 is VID by 2 and VGS2 is minus VID by 2 is reasonable assumption. We also observed that VGS3 is VGS4 or VGS3 if you have small signal, you look at, as I say, some books may show you. So essentially if the Vx is the output at node voltage, which is our Vout1, then it is GM VID, a combination of RO1 parallel RO3 parallel GM3, whichever will be smaller will be dominating. Okay. So I just right now kept all three in parallel, in reality whichever comes smaller among the three will take care, okay, 1 upon R plus 1 upon R1 plus, so whichever is smaller is the dominant term. So I just right now for the sake of simplicity or generality I put RO13 GM as the this resistance output, and then GM times this is there, so GM1 by, and if finally if that becomes GM3 dependent, which is the smallest among them, or GM3 is very large compared to RO 1 upon ROs, so GM3 will dominate, so you get GM1 upon 2 GM3 times VIT. Now this fact that this is the output of the first stage, that is M2 M1 M3, is going to be the input for M4, is what is going to be utilized to get the final VO value. Okay. So this derivation is necessary simply because this is going to be an input to the M4 at the other side. Okay. Is that okay? So this is what we did last time so far, maybe this expression I just showed you. So from here you can get, if you see a value of this, if you are holding the current constant as the ISS, then you can see from here it is only a function of W by L and mu, because 3 is p channel device. So it is essentially governed by the ratio of W by L and also mu n by mu p, all under roots. Okay. So we always know roughly how much is the size of the transistors, and we can get V out. Alternatively, what will be given to us? Given some final gains, we will have to come back and figure out what is the size of W1 by L1 and W3 by L3. But typical design, since all circuits are kept symmetric in most cases except for the perturbations they have, one can always say GM1 will be equal to GM2 and GM3 will be equal to GM4, okay. Or to say size of 3 and 4 will be same and 1 and 2 will also be same, except that they may have some variations even if we feel that we are done in the same technology zone. Okay. So that essentially is why CMRR comes finite, otherwise it would have been infinite. Okay. So this is the only criteria you should look, that this is a size dependent gain, it only depends on the sizes of the two transistors. As a designer, my only interest is in getting the surface sizing, okay, because these are called mask in fabrication. So for each layer, what should be the channel length, what should be the channel width, that mask which I will create at the end for the gate is going to decide my performance. So please remember, my output is only sizes. Okay. Given a circuit specification, I must arrive at the sizes of every transistor, because when I translate them into a circuit for fabrication, I will have to generate layout, that layout will be depending on W by Ls which I create, and those will be then transferred on silicon during fab, and hopefully chip may work. Okay. Normally it may, larger the technology node, more guaranteed it will work. We will see today, if time permitting, if short channel happens, what is the major worry with us. There are many worries, but one of the major worries I may show you. So is that okay? So I can calculate the input to M4 or to say output of the first stage, which is VO1. Now looking at the output side, the second part of the circuit, we know Vout is output voltage with minus VID input and VO with VGS4 as the another input. Okay. So we just superpose them. As I just now said, the method is open a current source, use the only one of them, open the other one and start looking for the other current source. So if I do that by substituting all this, it will become Vout will be GM4 RO24, where RO24 is parallel combination of RO2 and RO4. Is that clear? This is a shortening writing. RO24 is nothing but parallel combination of RO2 and RO4. That is at the output side. What is the impedance you are seeing, output impedance? Parallel combination of output resistance of 2 and 4. I repeat what I said, if you see the circuit, these are the only output resistances are in parallel. RO due to this, RO due to this, which are at this node are parallel. Is that okay? RO here at the output, both are in parallel. Okay, because this is ground for AC, this is ground for AC, this is ground for AC. So these two resistances are in parallel for this node. Is that correct? For this node. As I said, since GM4 is not a diode connected, ROs will dominate. GM4 is almost infinite kind of thing. So it will not be. See, I have kept it there because in case tomorrow you do something else there, that term may there and automatically it will get cancelled if it is larger or smaller corresponding. In general I kept it, but as such it will not be there because it is not diode. For this it is GM3 is appearing, for this there is no diode connection. That is a normal transistor whose output resistance is just the RO. Same is true for 2, same is true for 2, okay. Unless there is a diode connection, the GM will not dominate. Is that correct? We have done that case for a diode conducting load, and that is what we proved that time. Okay, so I substitute all these values. Once again VGS4 is V out 1 minus this, and by substituting finally I get V out is equal to GM1 GM4, and assuming right now GM1 is GM2, GM3 is GM4, all p channels are identical or n channels are identical. That means what are identical? Their W bials are identical, their thresholds are identical. Is that correct? The identical word means the mu Cox is constant, mu n Cox is same for both, VTs are same for both, and W bials are same for both. This is essentially means identical. As I said, I repeatedly saying perturbations will take care only in the case of CMRR, because that is hurting us then, otherwise it shows infinite value, otherwise you can always assume them for equivalence of this. So if I substitute all this, you can see, of course this is not exactly what is given in the book, but you can write down V out is GM1 GM4 upon GO1 plus GO3 plus GM3. Many a times instead of using RO in parallel, it is much easier for us if we use GOs, because then you can directly add. Is that correct? Many a times for the circuit people, you should realize that if they are in parallel, R is in parallel, it is much easier to add G's rather than putting 1 upon R plus 1 upon R plus 1 upon R. So I normally suddenly convert at times, so please do not feel anything wrong. This is just the way of solving simplicity, using simple solutions. So GM1 by GM2 upon GO1 plus GO3 plus GM3 plus 1 upon GO2 GO4 in plus the second term, which is for the VID by 2, is GM1 by GO2 plus GO4 into VID by 2. So once I get the relationship V out and VID by 2, I can always calculate V out by VID, which is essentially the gain of this single ended differential amplifier in difference mode. Is that correct? This is not a common mode gain, it is difference mode gain, AVDM. Okay, this is essentially a AVDM case. Okay, so please write down if you wish, because I am not sure whether this is given in Radavi, because I did not check, maybe there. Okay, at least they do not use G's the way I use. Of course I also, when I see that book, then I see, oh, they are using different terms, but I feel it is much easier, instead of RO write G's, which is easy to add. Of course this method of writing G's have come from my other colleague Professor Sharma, who has very fond of conductance rather than resistance. Things which can conduct is what all electrical engineering is about. If it is stopping it, then it is not good, na? So I think I also once in a while take his cue and I use G's, because I see in almost all his analysis he rarely use R's, he always write 1 upon G or G. So I figured out that I should also follow after so many years of my friendship, 35 years. Okay. So I just make a fun of it, nothing very serious. Is that okay? So I divide this VI2 by VID, and then I get these expressions, and then I start putting GM3 is much larger than GO1 or GO3, and therefore I neglect those terms. So I got VIO by VID, which is GM1 upon GO2 plus GO4. Okay, and if I is that clear? If I neglect these two terms, this becomes 1 GM3 by GM3, this becomes 2, this 2 cancels. So GM1 upon GO2 plus GO4 is essentially your difference gain. Maybe I should write AVDM. So which is, what is GM1? Why I wrote this expression is relevant for us, because from a designer's point of view, let us say what is GM1. GM1 is substituted as 2 times current in the each arm is ISS by 2 W by L1 into beta n dash divided by lambda 2 plus lambda 4 into ISS by 2. Okay. Lambda 2 and lambda 4 are not same. Why? 2 is n channel device, 4 is a p channel device. So lambda is not identical for n channel. Of course you can make this in process forcibly, but in normal circumstances lambda 2 will not be equal to lambda 4. They may not differ drastically, but since the mobilities in p channels are lower than n channels, normally resistances are higher in p channels once a while you think of it. So it may be better to use p channel as loads, is that correct, because it will give larger resistance per se. Okay, the issue here is lambda 2 by lambda 4, ISS by 2 I took it up, so it is beta n dash W by L1 by ISS. And what is the output resistance? I said you do not have to put a source and measure because it is obviously visible in calculation, so it is 1 upon GO2 plus GO4, maybe I should write GO4, which is like this, and case, which is what I say normally may not be, but if case you make lambda 2 equal to lambda 4 lambda, this will become lambda ISS, which is same as what we had derived earlier 1 upon lambda IDS. Okay. So once we get output resistance, we get the gain, the two major specification for DFAM have been found out, and they are functions of what? The bias current and the W by L's, is that correct? The bias current and the W by L. So you have as a design parameter with you, there are only two parameters governing the gain. One is the size of the M1 M2, and which is same, which is essentially governing GM1, okay, and the bias current ISS, which is also controllable externally, is that correct? Either by the transistor which I will put for source ISS, either the size of that transistor or the bias of that transistor, or I mirror it from some other source which actually will for exactly the current which I wish. Okay, I will show you mirrored ones later when I calculate. So essentially I am trying to tell you that the designer, I now have related, okay, if you want so much gains 10 to the power 4, 10 to the power whatever number you say. Also in many cases in books, we should know this, the gains are always specific, voltage gains will be specified as voltage by voltage, though it does not mean, because it essentially is trying to tell that it is both dimensions are same, but it is written V by V. Why? Because it is trying to show you it is a voltage amplifier, is that correct? So you also should get imbibe this, because there are 4 kinds of amplifiers which we can use, we all of you have gone through this earlier: output current, input voltage, output voltage, input current, input voltage, input currents, and output input voltage, input output voltage. So 4 passes. So it is called trans conductance, trans resistance, current amplifier, voltage amplifier, all 4. Okay, is that clear? So this is essentially what we are doing, and therefore we say that this V by V only tells input is voltage and output is also voltage. Okay, so I did not write, but I just thought you should know many books or many places the data sheets give V by V. So what is V by V? It is trying to tell you it is the voltage gain dependent terms which have been specified. Sometimes they may write V by I by V, I by I. So these are the methods of representing the amplifier outputs or gains. If we further make an assumption, which we will, we know that the p channel devices are same and n channel devices are also identical to each other, which they will be in most cases. We are now saying it means W by L1 is equal to W by L2 and W by L3 is equal to W by L4. This is not a necessity, but it is much easier to lay out, much easier to derive if these are available to you, but that is not a necessity. Expression does not require anything equivalence of that. If they are different, we can calculate with all different RO, different GM, so what? I mean, there is nothing very seriously problematic for getting all difference, but in normal case DFAM design on an integrated circuit will give you this GM1 very much same as GM2 and GM3 is very much same as GM4. Okay, in which case one of these sizes, if you figure out 1 and 3 or 2 and 4, you will be able to. So why I am telling you this word 2 and 4 is related to output resistance. So some way if I am giving you a IDS, I am actually giving you some way W by Ls, okay, indirectly, okay, 2 and 4. But if I know 2 and 4, I know L1 and 3 as well. Okay. So this is the design issue from what data is given to you and what specs are given to you and what is expected out of you, then you can figure out which term is. I will show you today at the end some few expressions when I design things something, okay. So is that okay? But I repeat, this is not a necessity, this is just for the heck of it, and in general I see people believe that it should be symmetric as much as possible, they try it, but that does not mean it is a necessity as far as the gain or any of the parts are concerned. There is a problem why it is normally kept, which I did not say so far, is there is an issue of stability of an amplifier. If they are not equal, the capacitances will not be equal, and there is a possibility of two stage amplifier oscillating. Okay. Having done this small signal analysis all through, let us look at little bit carefully other two or three parameters which are essentially large signal parameters. What does that large signal means? If the input voltage is not only restricted to VID by 2 and minus VID by 2, okay, if they exceed, what would happen? One of the major worry of any amplifier is, and that question was asked and I think most of you must have written correctly, that we are looking for large linearity, that is VO VN relation should have stand unity or whatever number for a larger input voltage swing, is that correct? If that happens, then we say we have input swing can be larger, so larger inputs can be amplified, that is called large linearities. We also want, as I said, we do not want linear mode because transistor is in linear mode is non-saturation, so square law terms will not be possible and it will give lot of distortions. So that question which was asked is large linearity, but device should still remain in saturation, and linear mode means it is in non-saturation. We have already shown VO VI characteristics. If Vn is outside the slope part, the VO is not even sometimes governed by Vn, it may become constant, okay. That is exactly what the saturation part appears there. So this issue we will look into this again. We want to see the limits, okay. So these are called limits or ranges. Two ranges of interest to me, one is at the input, the other is at the output. The output voltage maximum to minimum what I can get is called the output swing, okay. So one of the spec of a difference amplifier, or for that matter op amp, is the output swing, how much output maximum you can achieve from a given circuit which you design, okay. The other of course is how much maximum to minimum input I can vary which will still give me gain, is that correct? So what does that mean? The device still remains in saturation for those inputs, beyond that they may not. So I will figure out where they turn over from non-saturation and then say okay, this is the limit for me, okay. Now in some cases that limit may still have distortion because the linearity may not be as good, but does not matter, you may actually tune some of the distortions or you may tolerate some of those distortions, okay. Which distortion is most important? Third harmonic distortion. Think of it, why THD is most dominant distortion problem than the second harmonic which most people first derive, but it is the third harmonic which essentially is the trouble creator. So linearity is to be such that the third harmonic distortion is small, okay. So we will see that when the game comes, okay. So here is an amplifier again, same thing which I showed. Now let us say case, I just tell you how the data can be given to you, this is not being used specifically here but just to show you. For let us say I have a 5 volt supply, this 5 volt supply has come from 0.35 micron process, okay. We used to use 5 micron. So all the books whenever you see, barring the latest ones which may probably have 1.2 volt supply, otherwise this is the data given by everyone. So I thought if at all someday you are going to read the book, you should have this, okay. The VDD is 5 volt, VTO of enchant, O means stand for without substrate bias, typically it will be 0.7 volt, let us say plus minus, this is the tolerance you will get actually. Similarly VTOP will be, assuming right now we are using the same, I mean many technologies allow that, minus 0.7 plus minus 0.15, and for this 3.3 micron 0.35 micron technology you can use beta and dash, which is mu and Cox. This data of course I will provide you, whichever technology file I will use, the data will be coming from that technology file. Okay. But as far as we are right now concerned, it's the numbers are only numbers. Okay. We are not saying that this is specific to a technology. We may say okay, this is the data, okay, or this is the spec. In reality SPICE will not allow you random numbers for a given node, they will specify each of them because their oxide thickness are known, their capacitance are known, they know everything there. Okay. So they will specify automatically these values which you do not have to even worry, but if you want to read they will show you also what are the values they have been using in this. So typically beta and dash is used 110 microamp per volt square. Please take it, units should be correct in every sense because this is something I do not like, people do not putting any units. Sometimes I also forget, but if I do I write because I am a teacher, you are a student, okay, you have no rights. Okay. So this is microamps per volt square, beta p dash is chosen 55, what is that means, half of that means the ratio of mobility is chosen as 2, okay, mu n by mu p is 2. If they specify something else, obviously these numbers will also change. Okay, there is another number which is what we are going to use, is called input common mode voltage, which is defined as VICM, and typically for this supply, okay, we will come back this VI, this is what one of the things which we want to calculate right now or evaluate, but right now assume it for this is roughly 2 volts which is fixed. W by L for all transistors chosen here are 2, okay, no reason, just that, is that okay? So if I use this, okay, I mean this is a data probably I may use in my problem, so that is why I give you data, it is not that this data is very relevant data or something, this is typically for 0.35 micron, most people believe this is okay values. Okay. In reality the table from SPICE will be made available to you, whatever specs they get it they will specify. Okay. So those values are only arbitrary from my side, but they will give you exact values. Many books actually gives you data files. Okay. If you see a book they will, for a given technology they will give you tables for all parameters, TOX, everything, whatever, and variations, everything they will specify. Okay. All CGS, CGD, every capacitor, everything they will specify for you. Okay. Of course per micron they will specify because width will change the net capacitance, but they will specify all data file will give every detail of that. So please, if you have already done NG SPICE or whatever SPICE, see a technology file there and you will see all these things are provided by them. Okay. There are of course the Spectre or SPICE does not allow so much easily, but there is a model card in SPICE which you can write yourself. So it is not that what their default values are there, you have to only work with it, you can change your model parameters and still work on it if you have used model card of your own. So do not come and say ki sir wo to fix hai, you can always change your spec of your choice by putting another model card there. I am not sure with NG SPICE or SPICE 2G 3.3 has that, but just figure it out. The model card allows you to specify all mu's, TOX, everything of your choice. Okay. So please take it, these are some issues of interest. This figure is very important, I think this is what we are going to explain once again. If I plot the V out versus input VID, I figure it out from here, this minus VID by 2 somewhere if you look at it, very even up to minus VID by 2 there is some slope, beyond that it becomes almost constant, is that clear? So we say okay, what should be up to this or up to this, what should be the range up to which device can be treated in saturation. So here is the figure which we have plot. This need not be exact numbers, but just to show you, if I see from VID minus somewhere close to V out of 1 volt, for example, for VT of these values around 0.2 VID or something, it starts climbing. At this value device enters saturation, below that device is in non-saturation or linear mode. This active word is used by analog people very much in a wrong fashion, because active essentially is saturated mode in MOS transistors, okay, because that is the time where device amplifier is active. So I think this active word is not very true, but you should, maybe we should write non-saturated because that may create some bias. Okay. So similarly, if I see go beyond from 0 towards plus VID, somewhere close to this value of 0.2 or something VID, I figure it out at around 4 volt of output, the device enters non-saturation. From where this value is again, VGS minus VT exceeds VDS or less than VDS, as long as VGS is large. So we have now said gain can only occur when both M2 and M4 are in saturation, okay. At the output M2 and M4 are the two transistors, so if they are not in saturation, this RO parallel, this will not be there, GMs will not be there, and therefore, by the way, you calculate GM linear and figure it out why I keep saying it is much lower, okay. Otherwise you say why kuch to GM hai na, but that is much smaller than GM sat, and therefore this is the game. So we say now we start looking into that, please keep your figure up there, I will keep figure for myself here. We would say if VDS for the M2 transistor to be in saturation, VDS2, which is the drain to source voltage of that transistor, should be larger than or equal to VGS2 minus VTN. Is that okay? VGS2 minus VTN. This is straightforward transistor theory. However, if you look at the VDS2, it is nothing but this voltage minus Vs, call it okay, this you call Vs2, though they are equal, but these are voltage at the source, okay, which are grounded, but let us put them there, okay. Okay, so I say okay, then it is V out minus Vs1 is my VDS2, which should be greater than, now this is very interesting, the VG, this VG2 part is essentially the maximum input available, and from where saturation is guaranteed is VID by 2. So that is the swing available for you, VICM is the end of that, and VID by 2 you are going to put. So what is the range in which, because we are finding bound, so what is the maximum available to you is this much, okay. So if I do that analysis, so I say VICM minus is actually VG2 minus VS1, this is VGS2 minus VTN. But have you, yes, what is VICM? It is the input common mode range, maximum and minimum range. So if you are away from VID by 2 up to which transistor remains saturation, the test we are giving, but it will still require one VID by 2 to turn it, I mean to have a signal. So the difference available for me to see whether device still in saturation is VICM given to you minus VID by 2. Since VID by 2 is this, but essentially the transition occurs very close to 0 itself, so that term can still be neglected by you, but just to say that it is there I kept it. Normally books do not put that term, they say it is VID, only VICM, but I say okay, in case you feel it, the reason why they are doing it, because the transition if you see is occurring very close to 0, okay, is that clear, and that is why they normally neglect that VID2 term, but if case you want to keep, you can keep, but that is smaller than other values, so it will automatically be numerically neglected, physically maybe accepted. Is that okay now? I always try to say people that why people are saying something in the books or otherwise, so explanation, there is nothing very great I am telling. Okay. So I wrote that if the transition sat to non-sat occurs very close to the 0 VID value, then we can neglect this term anyway. So we say essentially what we are saying, the V out should be greater than VICM minus VTN. Now similarly I can calculate the limit for, this was for M2, is that correct? This was for M2. Now I calculate when M4 will remain in saturation. So what is the criteria for M4 then? That the VDS4 should be larger than VGS4 minus VTP. Okay. VTP is the p channel threshold. So I say, and this has to be subtracted by numerically, so I put a mod, otherwise it will get added, minus of minus may get added, so I just put it a mod. So if that is so, it is VSG4 minus VTP, but let us look at the game. अब ये आपको तो ये वैल्यू से लेना है, ये इसका गेट है और ये इसका सोर्स है, तो ये जो है ये VSG4 ये है एक्चुअली. ओके, नाउ वी कैन सी फ्रॉम हियर VDS4 this value is how much? VDD minus V out, VDD minus V out. So I substitute VDS4 is VDD minus V out. Okay, it should be less than now because this is minus, is that correct? Change the equality. So V out source is, for a p channel source is power supply end. Why? Otherwise holes cannot come down. Okay, okay. So if I write this, then V out should be less than equal to VDD minus VSG4 plus VTP. I flipped the inequality. If I get this, how many V out I got it now? First I got it V out from the M2 side, the other I am now getting from M4 side. Which one you feel will be larger? Please remember, from the input side is coming from the ground side. Look at it, this is what input to ground, but this is what output to the ground. Okay, so it goes to ground, but VDD, ground is AC ground, but it is VDD. So always the output side has larger value from the VDD side and smaller value from input side or lower side, and therefore M2 decides the minimum value of the swing and M4 decides the maximum value of outputs. So if I do this expressions, which have you written down? If I do that, clearly the output swing of a diff amp is V out max minus V out min, which is V out max is VDD minus VSG4 plus VTP, V out min is equal to VICM minus VTN, and therefore please take it that this is what is the criteria I have come from, that M2 M4 should remain in saturation. So from there I derive these two values and say difference between them is the maximum swing output can have. This has some okay, ramification word was difficult, so it has an influence, okay, on the next device input characteristics, what voltage it receives. Okay.
So in this analysis, VSG4 has to be evaluated.
Yeah, we will. We are not. I have not said we cannot evaluate. VSG4 is known to us. V out 1. ठीक है ना, बट पहले वाले स्टेज पर उसमें तो GM G वो तो वैल्यू वैसे पता हो गई. Okay, you are right, I am not denying, but why I left this, because some what will be given to me and what will be right now I do not know, so I am keeping expressions as they are. Okay, when I evaluate I will figure out what is given to me and I will come back to the evaluate this value from whichever, either they may give me this or they may give me something else. So I will arrive at this value from, please take it, what is VGS essentially can be written as in terms of IDS is equal to Vt plus under root of these I terms you can always write. So whichever way I am provided VSG, I will be able to calculate anyway, is that correct? So right now I do not want to say what is that, you are perfectly justified in asking, but I did not evaluate earlier because I will see which way I will evaluate, is that correct? If I know that is this current, I will say I know how much is, because this current will be output current is decided by something which we will see now, okay. So that also may decide VSG4, okay.
In calculating the swing, we are not considering gain of the amplifier.
Gain is essentially is very small because the end we are looking at the end of the gains, linearity just going out of linearity. So their gains are anyway very small, is that clear? If you are in this range, then only dV0 by dVn is very large, but if you are here, you are anyway very small gains. So we did not consider, assuming unity gains, which is not true, but to some extent it is okay, is that okay? But these are bounds, we are not saying these are the values, these are the bounds up to which this swing can be off. Please remember, I have put larger or less than, I never said equal to, equal is the better possibility but may not, they should actually satisfy the inequality, is that correct? Okay. uh, so one swing one parameter of or one specification of DFAM we have seen gain, other we have seen the output resistance, third we have seen swing, and the fourth we will now see, which is what is called an input that VICM I use. So now I will derive that ICMR. Another important specification of a DFAM is called input common mode range, okay. Is that okay? So should we go ahead? A was output swing, so B is named as input common mode range. So what is the input variations you can have? From VDD to VG1 is one possibility, and from VG1 to VSS or ground is the other possibility. That is how input will vary, is that correct? Please take it, input will vary from source to the VG, VP to this, or from VG to VDD. As we did for output, same way we now do it for input side, is that okay, Raj? Okay, from VDD we can reach VG1 through M3 and M1. Please look at it, the figure again. If I had to reach here, I can say drop across this and subtract here, or add whatever signs properly I get. So one path is like this, which is the other path? Other is you come here and you directly write from here, okay. If you do this, so there are possibility of either this, but if you reach this value you can also reach from here to here. So VG1 can be attained through this way or through this way or through this way, which is actually these two are identical because this VDS will be related to VGD, okay. So either I come from here or I come from here, I have the access to reach VG1, and same is true for VG2. Okay, so if this is what I am saying, I have two paths. So I said, same way I said, there similarly there will be two paths for VG2. We can reach through M4 and M2. Is that correct? It's identical. जो इधर है वो इधर है. Each path will give us VIC max, and we will figure out whichever one is lesser, okay. That will be my range, because lesser, why I should choose? Because I am finding the limit up to which device will remain in saturation, is that correct? So I will figure out two VICMs, okay, and then I will say which one is smaller, that I will use. So here are the two way of doing it. Path 1, which is VIC maximum 1 is VG1 max. Please remember what is the input common mode value, which is the input maximum value available to you, which allows device to remain in saturation. So it is VG1 max. How much is VG1 from the figure? this value minus this value, so you reach here, okay, that means you reach here, minus this value, okay, minus this value, okay. So not minus, why you are climbing up, so it is minus minus, that is plus. So VDD minus VSG3 minus VDS1 plus VGS1 is VGG1 max. However, at the edge of saturation, what is VDS1? When this transistor is having, and this VDS minus VT or VGS minus VT is equal to VDS, that is the edge, the least value of that. So I write VDS1 is VGS1 minus VTN at the edge of saturation. So I write VIC max 1 is VDD minus VSHD, and I replace this VDS1 by this, okay, this substitute here. So I get this VDD minus VSG by 3 plus VTN is the value which I am going to get. What is that clear to you? What did I say? I substituted VDS1 in terms of VGS1 minus VT, okay, and then that VGS1 cancelled and only this minus this cancelled and VT became positive. So in terms, so it is VIC maximum 1 is VDD minus VSG3 plus VTN. The other path, which is part 2, okay, which is VDD minus VDS4, okay, this minus this drop, so you reach this output minus VDS, please look at it. What is the other path? I come here, VDS4, VDD minus VDS4 minus VDS2, once I reach here I just add VGS2 to come here or VGS1 to come to the other side, is that correct? So if that is so, I have solved now the other one. VIC maximum 2 is VDD minus VDS4 saturation minus VDS2 plus VGS2 is VIC max. But what is VDS2 at the edge of saturation? VGS2 minus VTN, okay. So substitute this here, is that correct? At the edge of saturation, which is the limiting point for, then the saturation will go. So that is the value I want, max I am looking, so the edge I am looking. So I substitute this VDS2 here, okay, magnitude wise, you are right, subtract VSD by 2, but it does not matter as far as the p channel device, everything is in opposite sense, okay, so it does not matter. Okay. So if I substitute now this, I get VIC maximum 2 is VDD minus VDS4 plus VTN, and but VDS4 is VGS4 minus VTN, but VGS4 is VGS3, we have connected them, okay. So I write VDS4 is VGS3 minus VTN and substitute that again here. Oh, yeah, sorry, नहीं, but VTP is equal to VTN, so it doesn't matter, अभी n ही रहने दो, वहाँ p लिखो पर यहाँ n रख सकते हो, okay. So VIC maximum is VDD plus VSG3 plus 2 VTN is the value of VIC maximum 2. So which one is smaller among the two expressions I derived? One is, what was the value I derived first one? एक मिनट यहीं होगा शायद वो, हाँ ये रहा, VIC maximum is VDD minus VSG3 plus VTN, and this other one is VDD plus VSG3, okay. So what I am trying to say, VIC max 1 is smaller than VIC max 2. So what is the VIC max we should use? Is lower one, which is VDD minus VSG3 plus VTN is the value we are using for VIC maximum. Input common mode range, which will allow the transistors to get output both sides and still remain in saturation, is this value, one of this value. which is the other value I am going to get from the ground side or from the source side. Is that okay method? So please take it, in all analysis of amplifier the max value comes from VDD side and min value come from ground side or VSS side. Okay, so let us derive the VIC minimum part. So what is the path of VIC minimum for either transistor? This drop, please look at it, from ground or VSS, this drop plus this, is that clear? This plus this plus this, so that is the only VIC available to you to reach to the VG1 or VG2. Okay, so if I use this, and we do not have to be, since we have VIC minimum is VG1 or VG2 minimum to VSS path, we derived VIC minimum is VG minimum or VG2 minimum, which is VSS plus VDS5 plus VGS1 or VGS2, because we are assuming VSS to be 0 anyway. Okay, drop at the P point is 0. So I get this value, which is VD sat 5 plus, if VSS is taken 0, then VD sat 5 plus VGS1 or VGS2, whichever way. Typically VD sat, please take it, VGS minus VT for the data given to you is typically the value which you get at the edge is around 200 millivolts. Okay, but this is again for the 0.7 volt supply. Okay, so one should not use 0.7 volt VTs. If you have another technology, this 200 millivolt is not true. This 200 millivolts, I just want to show you order in which these numbers appear. Okay, so VD sat is typically for 200 millivolt for the source which is used, current source. So we now define input common mode range as VIC max minus VIC min, and this is the value which you, please remember this normally will be specified by us, how much is the drop across the current source. Okay, that is VDS5 is normally specifiable. These will be given to you as technology parameters. This you will have to calculate from currents or voltages through whichever you come. This is given to you. So everything is given to you, so you know ICMR, or if I give you ICMR, one of the parameters which is missing can be evaluated. Typically VDD, VT and this will not be, only thing you will be able to evaluate is VSG3 or equal to VSG4 if I have specified you input common mode range. Is that correct? This is the range, so I am essentially specifying to great extent this value. Is that clear? कौन पूछ रहा था ना VSG3 कहाँ से, यहाँ से ला सकते हैं, यदि आपको ये स्पेसिफाई कर दिया जाए तो बाकी सब कांस्टेंट्स हैं, so we can always get VSG3. Okay, is that point clear? This is a trick in designs, which spec is given and which you have to evaluate. Please remember this VSS is 0 is not a normal case. In most op amps you will always have dual rail, so you will have VDD 2.5 and VSS minus 2.5, swing still may be 5. Why there is a necessity of putting a minus supply instead of, why not single supply 0 to 5 or 0 to 3.3? Why people in analog in specific always want to run dual rails? There are many other 4 reasons, but the major reason why we did was to reduce noise considerations. Okay, okay, is that expression okay? So ICMR is VDD minus VSG3 plus VTN minus VD sat 5 plus VGS1. Okay, so let us do the next parameter of my interest. I have done so many, I am now giving one by one all the spec for a given DFAM, and whatever I am giving from DFAM are almost true for every one of them for op amp, with few more with op amp. Okay. The next important parameter for me is this power dissipation. This also will be specified. From where this gets specified? Why should I specify power dissipation? Do you know from where this power is actually getting limited? You can say power supply, yeah, that is a great issue, but that is not the only reason. Temperature, So essentially it is decided by the change in temperature of the device, and we know around 150 plus the junction loses its junction property, and because of that no junction will remain as junction, versus the leakage current will go so high, it will be higher than the what we call diffusion current will be dominated by drift currents. So we want to avoid that situation. So what do we do then? How do I decide that? I say okay, how much is the sink heat sink I am providing for the chip, that is called the thermal resistance available for to the ambient from the source of heat. So I solve a thermal conductivity equation, continuity equation, and figure out for given thermal time constants, that is the conductivity of the materials I am going to have in series of them, and I figure out how much heat I can dissipate so that temperature does not exceed this. Delta T by delta P is called thermal resistance. Delta T by delta P is called thermal resistance. So I must know that for a given temperature rise with the available thermal resistance of the path, I know how much is delta P possible, that is P possible. So power is limited by the heat sink and not anything else. Is that correct? If you can remove the heat, you can guess from this, your laptops or nowadays iPads or whatever Android based any other handheld system, they have been very low in power for a variety of reasons, okay, but their not only their power supply is low, but the method they have used, the materials are much better heat sinking materials. Whereas in a desktop system huge fans are put, because SMPS at least जो main power supply वो खराब नहीं हो जाए सबसे पहले डर है. Do you know the motherboard is fixed with the SMPS used? If your SMPS goes, your motherboard also has to be changed, because the voltage we are using is so high for speed that we do not bother heat generation, but then heat has to be removed. Okay, that is the reason why power is essentially decided by the thermal gradients you create. Of course in real chip there are another problem, if thermal source is away from the actual ground this, and there are huge transistors at different sources, they themselves conduct across, and then there is a huge thermal pattern comes. So all device properties are different at different point of time, and one does not know what characteristics will go. Okay. So this is called thermal simulations. So one of the major simulation we do first in real chip design is to do thermal simulation, where the thermal patterns are. Okay. Microprocessor में ALU के पास ऐसा हॉटस्पॉट बनता है, जल जाएगा पूरा यदि उसको हीट नहीं निकाल पाए तो उसको डिस्ट्रीब्यूटेड सर्किट कर देते हैं कि थोड़ा स्प्रेड हो जाए. Okay, so power dissipation is the power supply multiplied by the source current, which is IDS5 in our case. Okay. Generally we will be given PD max, or we may say given PD max divided by the supply for the technology node will decide maximum current available to you. Is that correct? What is the source maximum current given to you is decided by the power dissipation for you. Okay, इससे ज़्यादा करंट कहीं भी फ्लो नहीं होना है. Please remember this is for one arm. In fact, if there are 5 arms you have to divide by 5, that is power in each arm you have to get, and then find the IDS5, because at any time gradient should not be created. Okay, so this is one term which is limiting currents. Please remember, if I change the current, what changes? Everything changes. So far whatever terms I derived, everything is related to IDS, okay, ISS, which means any change there will affect all other parameters. So we must guard that. The fifth or sixth whatever number I have made, the next parameter of interest to me is the slew rate. Okay. Now if you see a simple circuit shown here, this DFAM is driving a load capacitance of CL. Okay. So one can say slew rate is defined as how fast the output rises to the maximum or change from higher to lower or lower to higher. So essentially it is defined as dV0 by dt rate. If I multiply it by capacitance and divide by capacitance, I get CL dV0 by dt by CL, which is same as slew rate. But what is CL dV0 by dt is the capacitive current, and the maximum current available to you is IDS 5. Okay. We will show you why that is the maximum current in the capacitors. We will show you right now it is not so visible, but so IDS 5 by CL is the slew rate. So what does now I am going to get it? If I am given a specified slew rate so many microvolt per microsecond, 10, 20, 100 or whatever number I specify, as soon as I specify a slew rate to you and the load is given to you, I am also now giving you limit for IDS 5. So कितने जगह से लिमिट मेरे सिर पे आ रही है, वो गेन वाले कह रहे हैं कि इतना चाहिए, ये कह रहे हैं इतना चाहिए, ये कह रहे हैं इतना चाहिए. So which one I should use? Optimal, which satisfy most of them. Is that correct? Not all of them exactly, but close to that if you can get. So IDS 5 is a design parameter, and that is why I say normally I prefer GM by IDS design, because IDS is now your design parameter. Is that clear? Is that point clear? IDS decide, that is source current, decides how much is everything going to be, and therefore you must actually look for this value from variety of specification given to you. Slew rate बोला वो एक फिक्स करके गया, पावर बोला, GM बोला, गेन वाला और एक है, ये भी इतना भी नहीं. If you look at the frequency response, the bandwidth part, let us say for this all other capacitance are not very relevant, which may not be true, and this is the dominant pole. So the 3 dB value which is my bandwidth is 2 pi R out CL. So R out is this 1 upon 2 pi 3 dB, 1 upon lambda I. Okay, what is lambda? What is the R? 1 upon lambda I, वहाँ भी आएगा. तो इस R out को यदि मैं अपने इस ट्रांजिस्टर के हिसाब से लिखूँ, so it is 1 upon GO2 plus GO4 or lambda P IDS 5 by 2. However, the difference gain, if I now substitute GMR this like this, which I had derived, now I can see from here IDS 5 can be evaluated from power supply requirements, that is power requirement, slew rate requirement. I may choose one IDS 5 and then start looking for the gains, the power dissipation, the slew rates. Is that clear? Once I fix this, then I will compare with my specs given, then I will tweak, okay, change this, that is what, and that is why I keep saying nowhere the gains will be specified as 1000, greater than equal to 1000. Okay, so you have play enough. Slew rate will be also said not less than so many microvolt per microsecond, not less than. Is that clear? Same way power dissipation maximum allowed is this. Okay, it does not mean you cannot have lower power dissipation. It does not say gain should not be more than what you specify. It says it is the bound which I am giving. The designer should choose values which suit therefore all specs as much as possible. Is that clear to you? So IDS 5 being my design parameter, let us say if you fix something and your gain does not come what is being specified, so increase W by 1 L1 is one possibility, or increase the IDS 5 itself. Okay, if you increase W by L1, indirectly you are also increasing IDS 1 which is connected to GM1. So please verify which term GM by IDS I told you now. Please take it GM by IDS I am looking into, this will decide my GM part, IDS will be decided by the other three. So my design parameter therefore is GM by IDS, not GM, not IDS, though I can independently look for them, but the ratio should be used by me as my design specification. Is that clear to you? GM is W by L1 related, so उसके size किया मुझे मिल गया. Okay, but IDS, so that you get the gain, you get the slew rate, you get the power dissipation, you get every spec which you want to attain to this. That is the minimum value which is allowed. So he is wrong. It should be higher than that. Anything which is higher slew rate I am not worried about. This is the minimum value I must attain to. Okay, think of it. Slew rate is always specified not less than so much. Okay. The minimum value of slew rate is 40 millivolt microvolt per microsecond. Okay. Okay, so is that point clear? As a designers, what is the criteria I am saying? GM and IDS ratio is I am adjusting, is that clear to you? And that decides me almost all specifications. So as a designer I keep watching what parameters I should tweak so that I get whatever specification for an amplifier is specified, is that clear? So difference between analysis and design is clear. In analysis we have derived the expressions, but we never look back and say why, what should I do. Now here we shall go back and see, oh, if I change this what will happen, if I do this what will happen. So I design, okay, I design only on 2 such things and I'll be satisfied. Before we quit for the day, we'll solve one problem, at least expressions I'll give you again. Since we are now going to now even 0.35 is a short channel device, but 90 nanometers below is certainly very short channel device, and the current technology of RF and digital is around 45 down. So many worries are there, but one of the major circuit worries is what I am looking into. Of course there are variation in mobilities because of mobility become functions of fields both Ex and Ey. So gradual channel approximation is no more valid. Depletion approximation is also a pseudo approximation. Vt reduces with reduction in channel lengths. Please remember, higher the channel length Vt is nearly constant, as channel length goes down Vt keeps falling. Okay. Then the worry which is most me is the third one, which is increase of Rs and Rd, source resistance and drain resistance of the source drain areas. As everything shrinks, rho L by A actually increases, is that clear? Because that increases, that series resistance of source and drain is one of the major worries. Of course there are huge problems in leakage currents, but that we will see later, is that clear? So there are, of course there are many more short channel effects. Right now I specified this. From the circuit point of view, I know even if it reduces I know how much, mobility changes I know for that how much, so I am not worried too much on them, I am designing with base. But this something I have not earlier calculated, now I may have to. See, remember mobility and Vt's are still difficult values, but they will be specified for a node, okay, so which is not in my hand, but I know, okay, I have to work with this. Leakage current is also technology dependent, of course is circuit dependent also to great extent, but in that case at least we are designing from the process itself to minimize the leakages. This something is not taken care in long channel, and this is the only one which I am going to show you. Please do not think there is no influence of others, everyone is influencing badly, but the one which I can immediately see my worry is this. Do you believe short channel device will be better or a long channel device? Okay, the criteria is the linearity, because amplifier what is important? The linearity. Do you believe that the short channel device will be more linear or larger linearity than the long channel? What is your idea, concept? Okay, the drain resistance anyway adds up to the drain value, Ro plus something that is small, we do not worry too much. But if the source side has the resistance, this Rsx is the source resistance of the M1 and M2, what do they act like? Source degeneration, is that correct? Great things happen. Okay, so let us do for a normal this device we have done it, VGS1 is Vtn plus 2 IDS1 by beta 1, no RSX used right now, but anyway VGS2 is Vtn this. However, VG1 minus VGS1 minus IDS Rx is the value now, this value was not there earlier, in short channel this value appeared, and that of course from the other side Vg2 minus Vgs2 IDS2 Rx. Now we define a term IODS which is output current, difference of output currents IDS1 minus IDS2, and which we know is GMVID, okay, we know this, we have already calculated. So what is the measure of linearity? Whatever is the input current change, how much is the output current change? If that is better, I say yeah we have better linearity, if not I would say it is less linearity. Okay. We want IOD proportional to I in, so if they are larger then I will say we are better linear. Is that expression all of you? Because GMVID is the current, the transistors converts voltage into current, so I will see linearity is only coming because of the current available. If current reduces, that is the VID term, we say the range ICMR, beyond that it is not linear. So we are looking for where up to which this relation is valid. Please remember this expression we will use often, VGS VTN plus under root 2 ID by beta is a very standard way of replacing IDS into VGS or VGS into IDS. Okay. This is a very standard technique. Okay. In a long channel device, please remember what is non-linearity of IO characteristics or VOVN characteristics is, can be done by Taylor series expansions. Okay. If I do Taylor series expansion, the IODS by ISS, if you want you can go read some papers, I have just copied from some paper, so just check it. IODS by ISS, VID by VOV. See, I am plotting the ratio of output current with VID. Is that transconductance word clear? Output is the current, input is the voltage, so I am just doing that. This is current which is actually getting at the output, ISS is the normalized current, and VID is your voltages. So IODS by S is VID by VOV minus half 1/8 VID plus higher terms. These two are good enough, cubic term is good enough. So if you are long channel device, this is the expression, is that okay? IOD by SS, VID by VOV minus 1/8 VID by VOV cube. However, in a short channel device, what should I replace now? This VOV will then become, because of the degeneration, 1 plus GM RS times VOV. We have done it earlier. I am just replacing source degeneration value. So the new value of VOV will be 1 plus GM RS time VOV. RS is the source current source resistance minus 1/8 of this. Is now, do you see the denominator is increasing in the this? Since the denominator is cube here and increasing, okay, short channel case different amplifier with RSX will show a better linear characteristics than the long channel device. What? That is true. See, what is design? If you achieve something, you lose something. Okay. But do you get the point? This was something which many people did not realize, that short channel device everything goes wrong, here is something can do good, okay, your linearity may improve, okay. And that is something why when a new design I start, I should look into whether which technology I am using and what linearity addition I got through. That has an advantage on output swings, okay, because some application may help you in that. Okay. Is that, you said na, someone said, मैंने last line लिख दिया, if IDRX drop will also reduce GM equivalently. Okay. So I am not saying that there is no penalty, okay. It is a penalty, but at the gain of linearity.